Today's lesson will be on a concept called recursion. So this is a little bit of a sidetrack from proofs. There is still one more type of proof we need to cover, but we're going to take a detour and talk about recursion first because it will actually help us understand our next kind of proof better. So what is recursion? This is something you might have seen previously in a coding class, but recursion is just basically the idea of solving a problem, breaking it into smaller problems. So the example I usually give to like start us off in recursion is factorials. So remember that just the definition of n factorial is n times n minus 1 times n minus 2 times all the numbers down to 2 times, multiplication, 2 times 1, right? So that's n factorial. And if we were going to do n minus 1 factorial, you see that n minus 1 factorial is similar, right? It'll be n minus 1 times n minus 2 times all the numbers still down to 2 times 1, right? So it's, it's just multiplying down, but starting at n minus 1. And so what you can see here is actually this portion here of n factorial is really just n minus 1 factorial, right? So I actually can write n factorial as n times n minus 1 factorial. And so the idea is that this is actually a recursive definition of n factorial, because I'm not actually fully, like in this example, right, I'm like fully multiplying it out all the way down, but this in this example I'm just expressing n factorial in terms of basically a smaller function. I'm expressing it in terms of n minus 1 factorial times a constant. And so this is the idea of recursion. You can just kind of it's basically a way of expressing your problem as like a different problem. And if you think about it in coding, it's usually going to be like expressing something as something else with like at least one smaller input. And so, that's generally the idea behind recursion, is that it's not fully computed out, but it's just maybe like expressed smaller, and then we can use that to compute it out. And we'll give more examples and kind of like go more into this definition in a bit. So first, I want to kind of talk about what it would look like in a program, because this might be a format that's more comfortable for you. And so what I did was I just defined this program called factorial. And so this is actually a function. So it takes an input, and so it's taking the input n. So it's basically just like the pseudocode we wrote, but I gave it a name. I called it factorial. Basically, it takes this input n, and if n equals 1, then it just returns the number 1. But otherwise, it actually returns n times factorial of n minus 1. And then basically, we're going to have to compute factorial n minus 1 before we could actually return. And so like we kind of think about what this would happen like for an input. So if I were to call like factorial on the number 3, let's say, right, I would step through my program, and so my input value, and I'm not going to do a memory diagram, which is something that you all might be familiar with, but this is something very similar to a memory diagram. If you don't know what that is, that's fine. But basically we'll be just setting input as 3, right? Because input is just this n we're inputting. So this is my input value. So I'm just setting input as 3. And so, this should not be input. This should be called n, because that's my name of it. So n is 3. And then I'm seeing basically if n equals 1, then we return 1, but n does not equal 1. N equals 3, so I skip past this if statement and I go to the else statement. And so since if wasn't true, I step inside my else, and it's telling me to return something. So I'm saying, okay, here's my return value. So I'm just going to put RV for my return value, and it's going to be n times something, but it's going to be n times factorial of n minus 1. So I actually have to call it again. So I have to call factorial now on n minus 1. So I actually have to call factorial on 2, right? Because my n is 3. So again, I'm calling, so before I can compute my return value for factorial of 3, I have to compute factorial of n minus 1, which is factorial of 2. So again, I can kind of like step into my program and say, okay, so my input, my n is going to be 2 this time. And if n equals 1, then that's my base case, but it does not equal 1. So I go into my else statement, and it says return again n times factorial of n minus 1. So my return value, I can't really compute yet, because I have to compute again factorial of n minus 1. So I'll just make another call here to factorial of n minus 1. Now that n is 2, factorial of n minus 1 is factorial of 1. And then again, I step into my program. I see my input now, my n is going to be 1. And now this if n equals 1, that's true. So now I actually step into my if statement instead of my else statement. And it just says return the value 1. So my RV is going to be 1, right? And now that I have that return value, that's basically like what I'm going to be inputting when I go back to factorial 2. So factorial 2, I'm returning n times factorial 1. So it'd be 2 times whatever was returned previously, which was 1. So it's going to be the value 2. So I'm just going to simplify it. Instead of writing it as 2 times 1, I'm just going to write it as 2. And then now I've returned 2. And then similarly for factorial of 3, my return value again was n times factorial of n minus 1. So it'll be 3 times factorial 2, which was 2. So that's going to be 6, 3 times 2. So my return value is going to be 6. And so my actual, like, what this function were to return, so if I were to say, like, print factorial 3, it would just print out this final return value. So it would just print out 6. That would be my output. And sure enough, like 3 factorial is 6, right? And basically what it did was it computed 2 factorial. And sure enough, 2 factorial is 2, right? So this is 2 factorial. And then it computed 1 factorial, which is 1. So that's 1 factorial. So basically it computes it all the way down into your base case, and then you kind of like plug it back in and work your way back up. And that's kind of your idea of recursion. And so the idea is that basically like your base case is kind of where you stop in your recursion, right? It was kind of like this last instance. So this is kind of where our recursion stops, and then we can kind of start working our way back up. So for here, our base case was this case. So n equals 1 is our base case. So when we have a value of, or, 1 factorial, basically, right? 1 factorial, that's our base case. And then every other time that we're just kind of like, if we're not at the base case and we're still just working down to another example, then that's going to be a recursive step or your recursive rule. Basically, like, how do I go to the next step down? How do I make this a smaller problem so I can work towards my base case? So like that's what I'm kind of like calling n times factorial of n minus 1. So I'm making the problem smaller by now calling the function on n minus 1 instead of on n. So making it like, calling it on a smaller version of the problem. And so that's basically like the idea of recursion. And so, I don't know, this if this version doesn't make as much sense to you, if you're not comfortable with the idea of code, that's fine. But I think this to me is probably the best way to understand recursion, is to kind of think of it as like, in terms of like function calls in a program. But we'll get more into like the more mathematical way of expressing recursion, because that's more what we're going to work with. So before we do that, I want to talk more about just why we use recursion in general. So sometimes it's because breaking a problem into smaller pieces can make it easier to solve. So, it is potentially easier to compute n minus 1 factorial than it is to compute n factorial, right? Like you have one less term to multiply, and then you can come back and multiply it. And so sometimes, for like a computer program, it's easier to kind of write a program that way, to kind of break it into smaller pieces. And it also can make it easier to reason about the problem. And basically, like this way of expressing a function, or we'll see other things we can express recursively. But expressing something recursively can kind of help us like break it down into smaller pieces, and that way we can reason about it, and then we can prove properties about it. And so sometimes like we can use that recursive definition. It makes it easier to prove things about the recursive definition rather than proving things about the like standard definition. Also, many programming languages are defined so that they heavily rely on recursive definitions. So some examples you might hear of are Haskell, Racket, Scheme. Also, if you go into like the formal methods area where you're proving things about like if you're doing more like mathy type of programming, you'll also see more of these types of programs. And so often these are called inductive type programming. That's just kind of like what they call these types of programs, but basically that's just another term for a program that relies heavily on recursion. But other programming languages also support recursion. I mean, so like the pseudocode I just showed you looked, it'd be pretty easy to translate that into a Python program and type that into Python and run it. And so the idea is that like programming languages, they still do support recursion, even if they're not like designed completely around it. So if I were to just have you like define recursion on paper, so this is like, we're defining just the recursive, like some function, but we're defining it recursively. This is what that would look like. And so you can do this for many different types of things. I'm going to show you the n factorial, so that's a function. But we also can do, sets, relations, tuples, lists, sequences, etc. And we'll play around more with those types of definitions in a bit. But the main part of a recursive definition involves first the base case. So basically that's like the initial element of what you're trying to define, and then you're kind of like building the rest of your function off of that. And so remember, for factorials, our base case is basically like where you can also kind of think about where your recursion stops. It's like the smallest instance of your problem. And so for us, it was when n equals 1, right? When we're computing the factorial, just 1 factorial. And the recursive rule basically tells you what to do every other time. So like your base case, again, is kind of like, if you're thinking about it like your function calls, right? Like your base case is down here, so it's where you stop. And your recursive rule is basically like telling you like these arrows, like how you go down to call each new function. So this is basically what your recursive rule is telling you. And so for factorials, so it's like, in the program, right, I kind of highlighted what the base case was and what the recursive one rule was for factorials. And so if I were to just ask you to write this out, it would just look something like this. It would say, you'd first do number 1, which is, or you could just do a bullet if you want, and write base case. And you can write it as 0 factorial, 1 factorial, not 0. A lot of times you will see 0 as a base case in a lot of examples, but for factorials, we stop at 1. So we'll do 1 factorial equals 1. Another way you could write it is if we did like do it in terms of like a function we wrote in a program. So I'll just say like, or you don't need to you could just do one of these answers would be acceptable. But so another way you could say it is like factorial of 1 equals 1. And then for your recursive rule, that's going to basically be telling you like how to take, just for a generic input n. So if I have n factorial, like how would I break that into something smaller? And so we kind of already showed it where you're just taking n times n minus 1 factorial. But like, so if you're doing it here in terms of your function, your basically your recursive rule would be factorial of n equals n times factorial of n minus 1. So either of these definitions would work. It's really whatever like makes you feel more comfortable. Because it's saying the same thing, right? It's just we're just kind of like writing out factorial differently in either instance. But this is an example of your base case and recursive rule. And so I'm just gonna kind of clean this up a little. So this could be considered an example of your base case and your recursive rule. And so if I ask you to define something recursively, this is what that would look like. So another really common, really famous type of recursion is the set of the Fibonacci numbers. This is like a classic example. And the reason is you can kind of like Google this, but the Fibonacci numbers can be used to describe a lot of phenomenon in nature. So like you'll often hear about like these articles of like, oh, math shows up everywhere. And a lot of times the examples will be examples of the Fibonacci numbers or like something using the Fibonacci numbers. So it's just a very famous sequence. And they're actually defined via recursion. So the base case, there's actually, what's interesting about the Fibonacci numbers is it has two base cases. And you'll kind of see why you need two base cases for the Fibonacci sequence in a second. So the base case is 0 and 1. So basically like the first two elements of the set of Fibonacci numbers. So you can think of it if you're doing your computing, indexing like a computer scientist, your 0th number and your first number of the Fibonacci sequence. And so the 0th number of the Fibonacci sequence is 0, and the first number is 1. Now the recursive rule is, that this should actually be n greater than 1, not n less than 1. So I'm going to fix that. N greater than 1. The Fibonacci f of n is basically just the sum of the two previous numbers. And so like we can kind of talk more about like, let's do some examples to kind of see what that means. So we have f of 0. I'm going to actually just write it as a list. So like the 0th index is going to be f of 0. The thing at element 1 is going to be f of 1. So that's 1. Right? So this is f of 0. This will be f of 1. And so if I wanted to compute the thing at index 2, it's basically so that if I'm using this like definition up here, right, f of 2 equals f of 2 minus 1. So that's f of 1 plus f of 0. And so f of 1 is 1, f of 0 is 0. So 1 plus 0, which equals 1. So f of 2 is actually 1. And then let's say I want to compute f of 3. Then again, I just, use my definition up here. So I say f of 3 equals f of n minus 1. So that's 3 minus 1 is 2 plus f of 3 minus 2, which is 1. So f of 2 plus f of 1. And then, so now again, I can just look and say, okay, f of 2 was 1. F of 1 was 1. So 1 plus 1 is going to be 2. So f of 3 is actually going to be 2. And then you just kind of keep defining it like so on. And so basically what it is each term is just the sum of the previous two numbers. So now you can kind of see f of 4 would just be the sum of f of 2 and f of 3. So f of 4 would be 3, and then right, because it'd be 2 plus 1. And then basically the next number would be the sum of these two numbers. So that would be 5. And then that's kind of how you would define your like the list, if I were to write a list of them, of the Fibonacci numbers. And so it's always defined this way. And so you can kind of see why you need two base cases. And it's when I was really doing, like when I was doing f of 2, right? I needed, remember like when I was doing f of 2, which was kind of like my first really recursive step, because I'm saying n greater than 1. So my first recursive step is going to be computing f of 2. And basically for f of 2, I needed f of 1 and f of 0. So that's why I needed two base cases, because like my definition, like my recursive rule, required two terms. So that's why I needed two base cases for this definition. So this is an example of how like your recursive rule can have, like, instead of just doing like, like the other example when I was doing factorials, I was just taking it and I was doing basically a constant plus a smaller version, right? But I'm not doing like 1 plus f of n minus 1 or something like that, right? I'm actually doing f of n minus 1 plus f of n minus 2. So this is kind of an interesting example because you're actually like expressing a problem using two smaller versions of that problem, right? Like now I'm doing f of n minus 1 and f of n minus 2. So this is just kind of like an interesting other example of how you can define something recursively. Like it doesn't have to be just like one smaller version. It can be like two smaller versions, and that's okay. In general, most of the stuff we'll be talking about in this course will be more of like breaking into one smaller version where it is going to be something more like, n times n minus 1 factorial or something like that. Like it will be more like where you're breaking into like one smaller version. But as you get farther in coding classes, you will be doing problems like this. Often, actually, like a common one is programming something like this, like kind of you can come up with smarter algorithms for it, and you kind of have to think about it in terms of like this kind of recursive definition. But for the purposes of this course, we'll be focusing more on like just the one smaller version. So another common example of like something you could define using recursion is power sets. And so this is just an example of how you can define a set recursively. So you can, and like, so the Fibonacci series is also like, it's a series, it's not really a set, but it's kind of similar. But we can define power sets recursively. And basically what you do is you just define like the power set of something. Like, so first of all, let's get like a little more used to this notation. So if you're adding, this is basically saying like a set plus an element, right? So like this would be saying like maybe like the set 1, 2, 3 plus 4, right? Like this would be my X. And then like 4 is my C. So like I'm adding C basically. Like I'm adding C inside a set. So C is an element, and then I'm just putting these squirrely braces around it so that way I'm adding like a set to another set. So basically I'm adding like one element to a set of elements. And so basically what it's saying is if I were to take the power set of X plus an element, then that's the same thing as taking the power set of X and unioning that with the power set of X. And you take basically every element of the power set of X and add that same element. So let's kind of like write this out, kind of, like an example of what this would look like. So let's do the power set. So like for our like X, let's make our X like something really small. So we'll make it like 1, 2, just the numbers 1 and 2. And so the power set of just 1 and 2, right? So this is my power set of X, is going to be the empty set, right? It's all subsets of this. So it'll be the empty set, and this is basically like a big set, right? So this is going to be an empty set. This is going to be just 1, just 2, and then 1, 2. And then I wanted to compute the power set of 1 and 2. So like now I'm saying like X plus C basically. And let's say I make C 3. So we'll make C equal to 3, and we'll make X equal to 1, 2. So the power set of the set X plus a set containing just the number 3, right? Just one element 3. Actually, so I'll say C right here, which is just, so this is the power set of 1, 2, messed up my notation here, 1, 2, plus the element 3. And if I'm using this definition, let's actually not use this definition yet. Let's first just do it how we normally would do a power set. So we could rewrite as 1, 1, 2 plus 3 as like the power set of just 1, 2, 3, right? Like we just added 3 to our set. That's basically like what this notation is saying. So I'm just rewriting it as the power set of the set 1, 2, 3. And so that would just be, similarly, we would just do like an empty set. 1, 2, 3. And then we have to do kind of like all size 2 subsets. So you have to do like 1, 2, and 2, 3. And then 1, 3. And then finally 1, 2, 3, right? You still have to include like everything's a subset of itself. So 1, 2, 3. Okay, so this is your power set of X plus C, right? It's the power set of just 1 plus 2 plus 3. But now if I were to use this kind of like recursive definition, I can also just write it using like my power set of X. So I'm going to change my colors so it's a little easier for us to differentiate here. So my power set of X, which was this, and so basically the power set of X plus C. So it's the same thing as I just computed, X plus C. And that, so it's going to be the power set of X. So I'm just going to start it as one big set because we're basically just unioning these two sets together. So, or I guess let's try this. So the power set of X, which is empty set, I'm just copying it over from here. 1, 2, and 1, 2. And then I'm unioning that with basically the power set of X, but every time we're adding the element C. So basically I take this and I add C to it. So the empty set plus C. I take this and I add C. So, sorry, C is 3. So I'll actually write the number 3. So I take 1 and I add 3. So I say like 1 and 3. I say take 2 and I add the element 3. So I do 2 and 3. And then I take 1, 2 and I add 3. And so that's 1, 2, 3. And then, so this is all like one set too, right? And so basically if I'm unioning these two sets, that just makes this like one big set, right? Because they don't have anything in common. So you could just kind of write these all within like one big squiggly line, right? So like these are like, this is the beginning of my set, this is the end of my set, and these are all my elements. And so this was just using like this definition, like using this right here basically to get this. But you can compare it, right? If we compare like the values, so empty set, like if I compare it to when I kind of manually did it, empty set, 1, 1, 2, 2, 3, 3, 1, 2, 1, 2, 2, 3, 2, 3, 1, 3, 1, 3, 1, 2, 3, 1, 2, 3. So you see it like it still has the same elements. So that just kind of like is just us just kind of like convincing ourselves like, okay, this definition kind of works. It's not a proof because, you know, remember we can't do proof by an example, but it's just our way of kind of like writing it out to see how this is kind of working. And so this is basically your way of defining power sets recursively, is you're like using that type of notation to define the power set recursively. And so like if I wanted to write this as like an actual recursive definition, I could do that. I could say like my base case would be like the power set of the empty set, which would just give you the empty set, right? Because it's kind of like the smallest thing that we could take the power set of. And then basically we can use this like recursive rule. So basically you can say like, so your recursive rule is basically like for any, let's write this out like in English, for any set X and any element C, then basically the power set of X plus that element C is going to be the power set of X unioned with the power set of X plus that element C. And so this is just a way you can kind of use like recursive definition, like now I'm using union instead of something like plus or things like that. But this is how like a set can be defined recursively, is something like this. And so an example we're going to work with a little bit in the lesson that you're going to be doing online is going to be this idea of defining lists recursively. And so this is basically I'm going to set you up, like we're going to talk a little bit about this example, and then like I'm going to have you kind of work on it on your own in the lesson. So let's just set up the example. So we're going to just define a list and some functions on it in a recursive way. So say all elements of our list are in set A. And so you can say like the set of all possible lists L is basically like a union of all kind of like element combinations of elements A. So it's all like, or sorry, not combinations, to be permutations, because we're considering ordering. So it's going to be all possible permutations of length K of the elements in A. And so this is kind of like how I would use my set notation to write that. Basically, it's like the union of A to the K. So all possible orderings of A, of like elements of A, basically. And it could be of all different lengths. So the length just has to be, greater than, it's going to be bound by some K, but it's kind of this K we're just saying is greater than or equal to 0. And so we can define this recursively. So we're just defining, again, like this is just basically the set of all possible lists. And so let's go ahead and do that. And so I'm going to define it using this function called cons for constructor. And basically the idea is that like cons, I'm actually going to just do it down here. So like the idea of this is that cons is like, again, it's your constructor. So it's like what you're using to make a list. And so like if we were to just combine it with an empty list, basically like the first argument in cons should be like what the new element we're adding to our list. So I'm just going to call that B. And since this is going to be our base case, we're just going to basically like add it to an empty list. So we can just make that like an empty set. I might just use a different notation so that way we kind of like are, because it's really a list, it's not a set. So I'm going to use like these kind of arrows. But you also could like maybe if you wanted to, you could use hard brackets, but then we don't want to get it confused with like, us doing like the kind of, the list ranges and stuff. So that's why I'm just going to do these kind of symbols. So that's going to be like my empty list. So if I take cons and I just want to add one element to my empty list. So this would basically be creating just a list of the element B. And so this is actually my base case. If I just wanted the list B, then I would just basically call my constructor with B on the empty set. And so if I wanted to do my recursive rule, the idea is basically, right, I want to be adding an element to an already constructed list. And so if I wanted to create the list, say, like ABC, basically what I would be doing is calling cons of A on the list BC, right? Like I would have my existing list BC and I'm just adding like A to the front. So that's kind of like how I want to define it. So for my more generic recursive rule is, say I have like some like already existing L, like or I'm gonna call this something else. I'm gonna do like Greek letters, I think. So I'll do like beta in L. So that's like an already existing list. So like you can kind of think of my beta as like the BC. Right? Like, and then I basically want to do like my element A, or I can do like a little element B that's in A, right? Because these are like the elements of my list. So this is also like this B is going to be in this set A. So I have my B in A. Then basically cons of like adding that one element to that existing list B, I would like basically write it this way. So I would like create my list this way. And you'll see like a more formal definition of this in your assignment, but this is basically the idea is like your like the definition of your base case would look more something like this, like cons is like in my set L, right? Like so cons B and the empty set is in my set L, and that's like my base case. And then basically like for like some already existing list beta, and for another element B, I could just basically say like cons of B and this already existing list is also going to be an L. Like, so if I wanted to create a new list, I just basically like I can create a new list by adding elements to it, which is true, right? That is how you would like create a new list, is you would keep adding elements to it. And so that's just basically what I'm saying, is I can create a new list by taking like an existing list and adding something to it. That's basically like what this recursive rule is saying. And so this is kind of like our, high level definition of a list. So this is kind of what you'll be working with. And like when you play around with it more, I think you'll get a better idea. And so like, let's just do like a little more practice with like the cons function. So we like are more comfortable with that. So we have like the idea of like cons of we had like just do the element 1 to the empty set, right? That would give us the list 1. If I did cons of I'm just gonna do like random numbers so we kind of understand, like 4 to a list that just has the element 3, that would just give me the list for 3, right? So I'm just putting this in the front, basically, is what cons is doing. Cons of 6 and 2 and 4 would give me 6, 2, 4, right? And so that just kind of getting an idea of what cons is doing. This is our constructor cons. It's just basically like creating a new list by adding an element to an already existing list. And so this is a recursive definition. And so again, you'll see like the formal definition of this in your assignment, but I really want to just kind of like get the idea of like what this what we're defining here. So let's go ahead and like define this recursively. So, or sorry, let's go ahead and like practice with some more functionality of this. So this is what we were just talking about, was our recursive definition. And so let's practice, like, now there's some partial functions. So remember, a partial function is just a function that doesn't necessarily like always for every input map to an output. But it should for like our defined set. So these are our partial functions because they work like with certain lists, basically, like with our lists, our set of lists as we've defined them. So I'm gonna talk about just some like useful partial functions we're gonna use. So there's gonna be two. There's going to be head and tail. And basically all it's doing is like the head of a list returns like the first element, and the tail of a list returns the rest of the list. So this isn't an element. L is not an element. It's returning the rest of the list. And so, you know, let's hammer that home. Head returns an element. And this returns a list. So let's kind of like practice a little bit with this head and tail. And then like, so I wrote my list as cons, right? But like this could be like, A could be the number 1 and L could be like 2, 3, 4. Right. And so if I were doing like head of 1, 2, 3, 4, I would just be like, I could kind of reduce the function back to like this cons format. So 1, 2, 3, 4 equals cons of 1, 2, 3, 4. And so I know head of this, so this would be, sorry, it's going to be equal to head of cons of 1 and 2, 3, 4. And so then basically that would just return 1, right? It would return this value. And similarly for tail, if I were to do tail of 1, 2, 3, 4, I could just rewrite 1, 2, 3, 4 using cons again. And then I'm just returning tail, and it's for cons AL, it's returning that second element. So it'd be returning 2, 3, 4. So I definitely recommend just like practicing, like even just with this format, now that you kind of understand more like how cons works, like just kind of practicing with different inputs for head and tail of lists, so you kind of understand exactly what head and tail are doing. But the main idea is that like head returns an element and tail returns a list. That's like kind of the most important takeaway you can have. Okay, and so I just want you to kind of like work more with that example in your assignment. And there's just one final note I kind of wanted to leave on. And that's the idea of strings and languages. And the reason I want to talk about this is we're not going to really use this in this course, but this is also something that's going to come up in your, mostly like in your like theory of computation courses. And so it's good to just kind of be familiar with these definitions. And basically, like, it's often kind of defined using this kind of notation I was using before with your lists. So you kind of have like this given alphabet. And often like it's an alphabet is denoted by sigma. And so similarly, how like my lists were made of elements from the set a string is made of elements from your alphabet sigma. And so like obviously like strings in the English language, like sigma could be made up of like, you know, of like A, B, C. But like your alphabet could also contain like exclamation points or question marks or quotation marks or something, you know? And so all that stuff is like in sigma. That's like making up your alphabet. And so you kind of just generalize it to a general alphabet, sigma. And so that's what a string is basically like made up of those characters. And so basically like the set of all possible strings that can be made from an alphabet, you'll see denoted as like sigma to like an asterisk. And basically this is kind of like hinting at that idea of like, remember how we kind of did like A to the K for all lists of length like up to K. So like for all, like this is for everything like for K greater than 0. So this is going to be like all lists of size K for like K all the way up to infinity. but basically like that's the same idea. It's like this asterisk right here is like basically like kind of meaning like infinity, basically. Like it's like you're approaching like it's like of any length. So like this could be like k, so this is like kind of k approaching infinity, you kind of think of it as. So this could be lists of length, so this kind of like includes like lists of length 0, and I'm like kind of using my union, so like lists of length 0, lists of length 1, lists of length 2, and so on, all the way to like, you know, whatever size, like they call it arbitrarily large is basically like the term they use. But it's like that's the kind of idea, is that this like sigma star, if they might call it, is just the set of all possible strings, and it's basically like kind of this exponential thing you're doing. So yeah, so that's kind of like that representation. And so a language is like a set L of strings within this alphabet. So like the idea is like if you're all possible strings from the alphabet could be like anything, right? So you can make like a string that says like exclamation point Q R W or whatever. And like that string doesn't necessarily mean something. So just because like this is in sigma star doesn't mean it exists in our language, right? Because like this doesn't actually have any meaning in English language. So basically the idea is that your language is a subset of like all of these possible strings. So that's just some notation that you will see in the future of like your computer science education. So I just kind of want to familiarize you with it using like this type of notation. Now that like we've kind of seen it for like our definition of lists, kind of like just a greater example of that. And so with that, that's our lesson on recursion. And you know, just make sure to go back to the definitions from the previous slides for cons to help you out with your lesson.